Okay, so welcome everyone to this new episode of VOILA seminars. I just introduce myself first and then a little bit of introduction of the series once again before beginning with our topic of today. So my name is Simone Vannuccini. I'm Chair of Economics of Artificial Intelligence and Innovation at the University of Côte d'Azur. And together with Lucia Satelli and Ekaterina Pritkova, together with also the FLA Côte d'Azur, which is the French School of Artificial Intelligence, we are the organizer of and promoter of the VOILA series. And today, we are meeting to discuss, after having seen AI and education, another topic for this fourth season, which is also the season that we constructed together with the audience. And today is the topic most upvoted by the academic audience, while last time it was the students. Today we meet to discuss AI and science and discovery. So that's a super important topic. And as usual with our VOILA seminars, we try to be both on the frontier of research and having topics that are accessible and inclusive, which is what makes VOILA somehow a unique offering in the panorama of, in the landscape of seminars on AI. And today, if my slides are moving, we have, as I said, it's time to talk about AI and scientific discovery, but before introducing the speaker, I would leave for a few minutes the word to Lucisa Satelli, that given that VOILA is a multilingual seminar series, will also introduce the series in French.
Thanks, Simone. Donc, juste quelques mots pour vous accueillir. Vous rappelez que vous avez la possibilité de déclencher les sous-titres automatiques en live avec le petit bouton qui est en bas de votre fenêtre Zoom, et qu'on est voilà, très, très heureuse et heureux avec Simone et Ekaterina de vous accueillir pour ce programme de la saison 4 de VOILA, qui a vraiment été conçu à partir du sondage que nous vous avions envoyé. Et donc, nous sommes très contents d'avoir ce talk de Jean Kossaifi sur IA et découverte scientifique. Back to you, Simone. Thanks.
Thank you very much, Lucille. So, as Lucille anticipated in French, so today we are very, very happy to have Jean Kossaifi, that, and I hope I pronounced the surname correctly, Jean, but in case, that is gonna introduce to us the topic of neural operators, a framework for scalable scientific computing. Now, Jean is a senior researcher at NVIDIA and also the lead at NVIDIA for AI engineering and scientific simulation. So we really have the crème de la crème, as I would say in French, for AI and AI application in the scientific domain. So Jean has also been receiving his PhD at Imperial College in artificial intelligence, and he's also very much a leader in open source AI, as you're gonna see. So I will not occupy much more time. The last piece of information have to do with our seminars in general. So Jean, please just a second more of patience. The first piece of information is that, as you know, now we have a new fully fledged and shiny website for VOILA. And now on the website, if you go on the website or you scan the QR code, you can just subscribe to receive the news about the new events. So this is not registration to the seminars, but it's just you can just give your email and then you will be notified when a new episode is up. So it's very low in terms of demands to you, but then you have a one-stop shop, so then you are notified about the new events. The second piece of information has to do with the structure of today's seminar. So we have today, we have 1 hour, not 1 hour and a half, so there will be no discussant, but we start with the talk of Jean for around 40 to 45 minutes. Then we have a bit of introduction to a Q&A, and then just question and answers. During the talk, yes, Jean has agreed to record, so we're recording the event. You, as Lucille already said, you have the possibility to translate the seminar in real time. Please do mute your microphones, but if you want to keep the video on so we see nice faces attending VOILA, you can, and you are welcome to. And also, if you have questions already, you can begin posting them in the chat, and then we will follow the order then for the Q&A. Very important for the PhD students that are registered on Adum, so that are getting credits for this seminar. As you know, log in. You should have logged in with the email you registered, and make sure that you have your name and surname here in Zoom, so that we can account for your presence and attendance. Okay, so given that, I am now leaving the floor to Jeanne, and we are very much thankful again for you joining us, especially because for you it's 7:30 in the morning. So I think you should be able to share your screen, Jeanne, yes, and also to unmute yourself, and then the floor is yours.
Great. Yeah, merci beaucoup Simone, Lucille et Katrina pour l'invitation. C'est un plaisir d'être ici ce soir, enfin ici virtuellement, pour partager avec vous notre travail sur les opérateurs neuronaux. And so yeah, the rest of the talk will be in English, don't worry. So yeah, I'm very happy to be giving this talk. It is 7:30 in the morning here, so starting with a coffee, and what better way to start the day than discussing how AI can help scientific discovery, a way to end the day for you guys, I guess. So yeah, as Simone mentioned, I'm a research scientist at NVIDIA, where we work a lot on scientific computing. And so today I'm going to present neural operator as a framework to do this. And so the first observation is that a lot of the traditional deep learning that we are familiar with were historically designed for a discrete world of pixels and words. So in language, for example, you have fixed vocabulary size and you're learning on discrete tokens. In images, you typically learn on fixed resolution pixel images. And as you may know, scientific data is typically a little different in the sense that we have different boundary conditions and different geometries, and that the interesting phenomena we would like to model happen at multiple scale, and they are governed by mathematical equations, so partial differential equations, in some cases known, in others not. So for example, you may want to use the Rayleigh-Bénard convection model if you're looking at the velocity or temperature of a fluid you're heating from below. You may want to model the flow, the airflow around the car to measure its drag, or we may be interested to actually predict weather. Given the current atmospheric state, can we look at what it's going to be like in a day, 2 days, 5 days, etc. And so weather forecasting in particular is a really interesting application for us. First, because it's an example of largely unsolved problem where we don't actually know the exact equations governing the system. So that's a case where we're really interested in potentially learning from data, which is, this is what AI really is mostly about, a lot of learning from data. And it's an inherently multi-scale problem. So if you look at the graph, you can see that depending on the resolution of the atmospheric state you're looking at, you can resolve different things. And so we need to be able to look at different resolutions to do well. And the problem is that climate and weather predictions are currently limited by the available computational power. So even if we continue to double the computational power every year, it would still take us over 10 years to get to a storm resolving resolution, not to mention, low cloud resolving. And so we need something to accelerate prediction beyond just hardware acceleration. And that's where we hope that AI, by developing surrogate model, can give us this additional speed up on top of hardware speed up. And the second motivating example for using AI surrogate models to accelerate numerical simulation is the fact that in many critical applications, like weather forecasting, we don't want to make a single best guess prediction, but we want to eventually reason and make decisions about a range of possible outcomes. For example, if there is a hurricane, what is the probability that it will create landfall in a particular region? And so this is typically done by running large ensembles. So you take your model, perturb a little bit the initial conditions, run it many times, and this kind of gives you an ensemble of possibilities. And so this makes the problem even more computationally prohibitive. So if your model already takes you, a day to run, and now you need to run 1,000 ensemble members, it just becomes impossible. So accelerating prediction and being able to reason about probabilities are two of the biggest motivations for using these models. And we really want models that can capture the complexity of scientific data. And so next, I'm going to talk about what such a framework would look like before I actually dive into how we implement it in practice. So the first thing is something I've already touched upon, and the fact that our data is multi-scale, and we need to look at different resolutions, and we want to learn not just a function, but an operator. And so if we look, for example, in physics, if you're familiar with physics-informed neural networks, that's an example where we're actually solving for a single instance. So you take one instance of your PDE problem, and you learn a mapping, for example, from the coordinate x, y, z to the solution at those coordinates. By contrast, what we want to do here is learn an operator, which means that once it's learned, you want to be able to give it any initial condition function as input and get the entire solution function as output. So basically what this means is we can now give to our model the same input function at different discretization. And so this becomes a little useless if the number of parameters grows when you change the resolution. So the next thing we want is to decouple resolution and number of parameters. And so an example I usually take is that of the simplest building block of neural network, the linear layer or perceptron, which basically learns a function, phi here, that maps an input vector, so a collection of endpoints f1 to fn, to an output, so an output vector g1 to gm. So here, if we look at one of those outputs, how do we obtain this? Well, we simply take a linear combination of our input points, weighted by some learned weights here, k, I, j. And so obviously, if now you want to learn on new points, let's say you, instead of having n discretization points of your input function, you want to add p new points, first you will have to retrain your layer. And second, you need to add new weights. And so in practice, if you look at a whole network, what this means is that your number of parameters would grow typically quadratically or even exponentially with the size of your input. So if you want to go at very high resolutions, your model becomes intractably large. So one thing is we want to decouple resolution and number of parameters. Once we have this, obviously, we want something that's resolution invariant. So you take your function. If you look at the same function at different discretization, you ideally would want your network to still work. You wouldn't want to have to retrain for each new discretization. And you want to be able to predict at different discretizations as well. And so this one is kind of a corollary. But once you have this ability to query and predict at different resolution, you want a property that we call discretization convergence. And all it means is that things stay consistent across resolutions. So if you're looking here, for example, at the airflow around an airfoil, if you're looking at the same airfoil and same conditions, ideally you would want your solution predicted by your operator to look still similar. You don't want to have different solutions predicted by your model at different resolutions. So this is all what we mean. We want things to stay consistent, and we want things to converge to a coherent to a limit as you refine the mesh. And so that's kind of what neural operators are mostly about. It's kind of looking at the continuum. Do things stay consistent when you change the mesh, and do they converge properly? So the last two properties are data efficiency. We often have very little data for those complicated problems. And universal approximation, basically, you may be familiar with this theorem, but it's essentially an existence proof, and it just tells you that if you have a neural network with enough capacity, you can now approximate arbitrarily well any continuous function. And so we would like to know whether there's such a thing for neural operators, so is it even worth it to try learning this? Spoiler alert, the answer is obviously yes, otherwise I wouldn't be here. And so how do we do this in practice? What does this framework look like? So just to take again the example of the linear operator, previously we were learning a function. Now we'll be learning an operator. So instead of mapping between finite dimensional spaces, we're learning mapping between function spaces. So a space of input functions to a space of output functions. And so we'll be mapping not vectors to vectors anymore, but functions to functions. And so once again, to take the example of the linear layer or perceptron, previously we were predicting our output by essentially taking a weighted average of our input points plus potentially some bias. So if we take this to the function space, to learning on function spaces, it looks the same, except now we will take our input function f and integrate it over its domain. And so we'll take the integral weighted by some kernel k of x and y. So it's a kernel that depends on the input coordinates, the coordinates of the input function and of the output function, plus again some bias. And once again, if you're given discretization, you get a weighted sum of your inputs, except now you have this learnable kernel, which is a function. And you have this delta x here, which you may have recognized the Riemann sum approximating the integral. And so these are simply the quadrature weights to make sure that it converges correctly. And so that's one of the most important things we do when we do neural operators. We make sure that things converge properly. And you don't want your convergence or your solution to depend on your choice of discretization. If you choose something naive, like you would do with a neural network, where you just take, let's say, equal quadrature for each weight, regardless of how you discretize, different discretization will converge differently. And so you really want to be careful about this choice of discretization in case some areas of your space are most densely sampled, for example. And so putting all of this together, this gives you the kind of foundational neural operator, where you start with your input function, which is given at some discretization. You have some encoder, which potentially can lift your problem to higher dimensions. And then you have a stack of these neural operator layers, which are some version of this linear kernel integral transform I just introduced, with some nonlinearity, obviously. So I'll cover in the rest of the talk how we realize this kernel integral. But basically, you stack a bunch of those blocks. You at the end have a decoder that projects back to your output space, and that gives you your output function. And so here, the key focus will really be what kind of form do we use for this kernel integral, and how do we learn the kernel? So I mentioned the approximation theorem. We have this, powerful architecture. And so the question is, is it capable of representing the operator we want to learn? And the answer is yes. This is guaranteed by this approximation theorem for operators that was proven by one of my colleagues, Nikola Kovački, which says that for any continuous operator, assuming a large enough neural operator, we can build a neural operator that approximates it arbitrarily well. So now we have a chance to learn our operator. How do we do that in practice? So I'm going to go over a few realizations of neural operators. The first one is if you're on a regular grid. In this case, you can look at a particular case of our integral linear operator. So instead of taking an arbitrary kernel, here we'll take a kernel x minus y, and so we'll basically do a global convolution in the physical space. And the convolutional theorem tells us that we can realize this in the Fourier domain. So what we do is we take a Fourier transform of our kernel and our input function, do an element-wise multiplication in frequency domain, and invert the transform. And an important thing is we want to decouple, if you remember, resolution from parameters. So we will project to a fixed basis space. So in this case, it will be Fourier basis functions. And so what it means, we will truncate in the Fourier domains to use a fixed number of bases. So now if the grid is regular, you can realize the Fourier transform very efficiently with a fast Fourier transform, FFT, which buys you an O of n log n complexity instead of O of n squared. So it will just be a lot faster. And so in this case, what we do is we learn the kernel directly in the spectral domain. And then you take your input given on a regular grid, apply FFT, do an element-wise multiplication, truncate the high frequencies, do an element-wise multiplication, and do inverse FFT. And so your block is basically just this, plus some residual connection that will recover high frequency information and non-periodic information. And so this is just an example of such an FNO, Fourier neural operator, trained on a Kolmogorov flow. Here it was trained on an input resolution, 64 by 64, and we inferenced it at higher resolution unseen during training. And as you can see on this energy spectrum, it actually learned quite well to match the energy spectrum, even on frequencies that were not seen during training. While if you were to interpolate your input to feed it to a pre-trained neural network, it doesn't really know what to do with those new frequencies. So that was for learning on the plane. Now, what to do if you're on the sphere? And so a case I mentioned before is weather forecasting. And so in NVIDIA, we built back in 2022 ForecastNet, which is a data-driven model based on the FNO. And the goal, again, is to use to learn data-driven weather and climate prediction model to accelerate the process. So we train everything on a data set called ERA5. It's ERA5 reanalysis data, which is produced by the Integrated Forecasting System model and is considered as the gold standard for weather forecasting. It has over 4 decades of high-quality data, and it's all openly distributed, which is great. And so one advantage in taking into account the geometry here is that if you trained a transformer on the left, things quickly used to explode, a model that didn't respect the geometry, while the model, the spherical Fourier neural operator we trained, was able to stay stable for several months of rollouts. And so how do we do this in practice? Well, it's again the same idea as the FNO that I just present, except now we're on the sphere. So instead of using basis functions on the plane, sine and cosines, we will use circular functions or spherical harmonics defined directly on the sphere. And so the model looks exactly the same. You can once again see our kernel integral here that is just now adapted to do convolution on the sphere. And we simply will do either a global or local convolution on the sphere in the spectral domain with, again, some skip connections. And here we have some linear layers that will do channel mixing. And so, as I mentioned, we don't want to just do a best guess for the future state of the weather. We want to generate large ensembles. And so the idea is that the latest version of ForecastNet, ForecastNet 3, which was also led in NVIDIA by my colleagues Boris, Bonef, and Thorsten, is to make the prediction stochastic by injecting some randomness in the forecast. So you take as each step, you take the atmospheric state as input, as well as some noise variables, which we generate smooth random field on the sphere. And so you essentially add these perturbations to your model and you get some predictions out. And so at each 6-hour step, the network predicts the next state conditioned on the current atmospheric state, some auxiliary variables like solar, zenith, cosine, etc., and this latent noise field. What this means is that as you change this noise for the same state, you're getting multiple possible futures. And so how do we train this model? Because now we're not using deterministic forecasting anymore. We have several predictions. We use something called the continuously ranked probability score, which essentially is taking some average distance to the ground truth minus a penalty for being too spread. And so it's essentially says, so M here is the number of ensembles. So it says how far is each forecast to what really happens. And then here we have a term that accounts for how spread out the forecasting distribution is. And so this kind of encourages well-calibrated ensembles, which is a property we really want. And so the final loss is a combination of the CRPS applied in the physical domain and in the spectral domain. And so the result is a model that actually outperformed traditional numerical weather prediction models while being a lot faster. So this one in particular, if you run it on a single GPU, was 60 times faster than the IFS running on a supercomputer and 8 times faster than GenCast. And each of the ensemble members are physical in the sense that they have this right interchannel correlations and proper spectra, energy spectra. And so what does this mean in practice? If you want to, again, look at extreme weather events, this enables you to do much better risk assessment by better predicting the probability distribution. So here, for example, we're looking at, I think it was for Houston Hurricane Harvey. If you're looking at multiple predictions, and so here you have the wind speeds in meters per second. If you only can run 50 ensemble members, you get a very poor estimation of your probability distribution. And obviously, the more ensemble members you get, the better distribution you'll get. And the better you'll be able to capture here those tail events, which are really what we're interested in, because here they correspond to extreme winds. And that's really what you want to prepare with. So fast models will really enable you to get this better predictions, better assessment of the actual probability distribution. And the final case I want to mention is if you have a problem where you have to work on arbitrary geometries. And so car design is one of those. Ideally, you don't want to stick your new car in a wind tunnel every time you design it. So here the problem is, given an inlet velocity, we want to try to predict the drag and the surface pressure on the car. And so again, the idea is the same as what we've been doing so far. We still start with our kernel integral here, except given that now we have a huge point cloud, so we have a car geometry given as a collection of points, it would be computationally very inefficient to do a global integral. So we do a local integral, and we integrate over a local ball centered around our query point. So here we have an input function from the previous layer. So here this v of y, and we simply integrate over a fixed neighborhood. And so the advantage is this. This means that the domain on which you aggregate information is fixed regardless of the discretization of your function. And this is, again, an important point when dealing with neural operators, because imagine you're looking at the same function, and now you refine your discretization. If you rely on something that's nearest neighbors, like a graph neural network that typically looks at nearest neighbors for each point, as you refine the discretization, you basically, the receptive field will collapse to a pointwise operation. So it's really important to make sure things stay consistent. And so finally, the final architecture would look something like this. Once again, you take your input, you have here some encoder that in this case is a graph neural operator that will aggregate information on the surface of the car, and that we will query on a regular grid, because we can now query this model anywhere. So now that we have a regular grid, we can apply an FNO that's very computationally efficient because of the FFT. And at the end, we simply have a decoder that's, again, a GNO that will predict back our desired geometry. And so this is a cost accuracy trade-off for comparing the method with an open foam solver. And so here we basically increase the cost of the GNO by simply making the network larger. And so we were able to get similar accuracies with a 10,000x speedup. So in this case, you're really, again, able to get a lot of speedup over doing regular numerical simulation. And finally, in some cases, we do know the equations that govern the system. And so in this case, you can use it as a loss. So what we did so far is learning from data. You have a discretization of your input. You learn to map it to your output. If you also know the PDE, you can now take the output generated by your model, plug it in the actual equation, and do some instance-wise fine-tuning. So given a new instance of your problem, you can actually fine-tune for that one in particular. And so to take the same example as before, this actually allows you to match pretty perfectly the actual energy spectrum. So here, now the ground truth spectrum and the prediction by our model are superposed if we add this physics-informed loss. So that was an overview of how neural operator frameworks works, some concrete realization of the model for discrete, spherical, and arbitrary geometries. And so now I want to touch a bit about on scaling neural operators. As I'm sure you're all aware, scaling has become very important. And so I don't know if you've seen this paper, but it's the scaling laws for neural language models. And it's kind of the paper that, it's part of this bitter lesson that essentially, if you have infinite compute, or if you can increase your compute, if you can increase your data set size or your number of parameters, your model size, you basically get better performance. What this means in practice is you're typically then bottlenecked by your ability to do this scaling. And we found that this scaling is also true for scientific applications. And so one question is, how do we scale those methods? And there are a variety of ways. One is custom kernels. So for the spherical harmonics that I presented, for example, the initial implementation was really too slow to actually be trained. Triton was a lot faster, but still too slow to get us good throughput. And so again, my colleague Boris and Thorsten wrote a custom CUDA kernel that is really what enabled us to train this, because now it became manageable. The second thing is obviously, as you're scaling up the amount of data you're training on, you would want to do data parallelism. And if you want to scale the model size and the input resolution, you might want to do model parallelism as well, which is what we did for these weather models. And so the last two things are incremental training. So this idea now is that you have a model that can work across resolutions. You can apply it on data at different resolutions. So you can now train at a fixed low resolution, which will be very efficient, both computationally and in terms of input and output. And you can fine-tune on a smaller set at high resolution. And so this should speed up the model a lot by first capturing, global coarse dynamics and then learning the high frequency information. And the last thing I want to mention is tensor factorizations. I've worked a lot on tensor methods. I think they're really nice and useful in our field. And so you can actually use this to speed up the models. And so I'm gonna touch a bit on how. So just to give a very, very brief introduction to tensor methods, they essentially just generalize matrix algebra to higher orders of more than 2. So if a matrix is just a 2D array, a tensor will now be a multi-dimensional array. And you can generalize all the operations like matrix multiplication. In 2D, you can multiply a matrix on the left or the right. But in the tensor case, you can now contract 2 tensor along a shared dimension. And so once you're equipped with this, you can generalize concepts like matrix decomposition. So here, if you just take your input matrix and express it as a sum of rank 1 matrices, so just a sum of outer products, you can do exactly the same thing for tensors. That would be the canonical polyadic decomposition, where now you're expressing your input tensor as a sum of rank 1 tensors. So this is a low rank factorization of your tensor. Each one of those rank 1 components is an outer product of 3 or more vectors. And you can have more complex decomposition. Here, for example, is the Tucker decomposition, which you can think of as a form of higher order SVD, which here you don't have a diagonal matrix in the middle, but you actually have a dense core tensor, and you have projection matrices along each dimension. So you can now take a large input tensor and project it to this low rank space, because these projection factors are orthonormal. So this will be useful now because we can use this to do compression. And so one thing to realize when scaling is to actually look at what we want to scale. And a lot of people tend to focus solely on the model size, compressing the parameters. But if you look at this graph, model parameters are actually a fairly small fraction of the total memory. Okay, so this actually should be the gradients, not the parameters. So this lower green here is the number of parameters. Here, the optimizer state is typically larger than the parameters because you need to, if you're using an Adam optimizer, you need to store moments of your gradients, and so you end up storing twice as much parameters. And then you have gradients and intermediate results. And as you scale your model size, things become a lot worse. And so really what we want to look at here would be compressing the optimizer state. And the way we did this is we extended Galois to what we call TensorGrad. And so every time you have a gradient, we're going to decompose it as a sum of, so now our gradients, I should mention, are tensors, because the Fourier neural operator has a multidimensional data. Your gradient will also be a higher order tensor. And if you turn it into a matrix and decompose this, that becomes suboptimal. And so we really want to preserve this tensor structure. And so in this case, we take our input gradient and we decompose it as first a low-rank tensor. And then we apply our optimizer to the cotensor. So we do a Tucker decomposition. We project our gradients to this low-rank core I presented before, and we simply apply our optimizer to this small core. So now you're applying your optimizer to a much smaller set of parameters, so it will take a lot less memory. And then once you want to do your update, you reconstruct the full tensor. And here in this case, we also added a sparse part. So after getting the low rank approximation to the tensor, we also extracted some sparse components to try to make the decomposition more robust. So based on the idea of these robust tensor decompositions, we then get this sparse part and also apply another optimizer on this very, very sparse tensors. And so this allows you to basically reduce a lot the memory consumption. And so here this was trained on an HB200. So here you can see that the original memory usage was above 80 gigs of memory. So even if you have an A100 or H100 with 80 gigs of RAM, you wouldn't actually be able to train this model on Navier-Stokes, which was at resolution 1024 by 1024. And so if you don't have access to larger GPUs with more memory, you can simply apply this trick to reduce the memory usage. So here, the first thing you can do is mixed precision. So this H here just meant half precision. So you can use half precision for storing everything except your optimizer state. We found that if your optimizer state is in half precision, you will lose a lot of performance. So you can keep everything in half precision to reduce your memory usage, keep the optimizer in full precision. And this plus here is for activation checkpointings. So basically you have all these intermediate results. Instead of saving them, you can either recompute them or offload them to CPU. So this is this method. And then if you apply TensorGrad, you can reduce the optimizer size here, so this dark green, significantly, as I mentioned. And if you combine all of these tricks, you can now more than half your memory usage while actually not losing out at all on performance. So essentially, we have some tricks to improve to scale those models. So that was a case of applying tensor decomposition to the optimizer state. You can do something similar to the weight. So we had this paper of multi-grid tensorized Fourier neural operator, where you can apply tensor decomposition to the weights directly, and then optimize directly the factors of your decomposition. And so this also allows you to reduce number of parameters a lot. So yeah, hopefully that was a good overview of like how neural operator works and how to scale them. And so now if you actually want to try them, as Simone mentioned, I'm a big believer in open source software. I think a lot of this so-called AI revolution was made possible by open science and open source software. And so we really try to contribute to that. So all the works I presented here are actually open source. So these custom kernels I mentioned for spherical harmonics are available in the Torch Harmonic package. And we also open source the entire training and inference pipeline for this forecast-net model I presented, which is in this Makani code base. And more generally, if you want to try any of the new neural operators or any of the ones I presented, we have this library called Neural Operator, where we basically try to provide all of the latest neural operators we're working on, as well as all the tools you need to work with them. So it's a PyTorch library. There was the PyTorch developer conference in San Francisco yesterday and today, and we also presented it there. And the idea is you can simply plug it in your existing PyTorch workflow and replace any model with a neural operator. And it will work across resolution, and it will hopefully do things properly. So it is on GitHub. You can give it a try. And we also have products we develop in NVIDIA where we port all the mature technology, and that is very rigorously tested. So for people who actually need to maintain product, we have Physics Nemo that provides the core models, and then this NVIDIA Earth 2 Studio allows you to do all things related to weather. So yeah, just to conclude, neural operators are basically a rigorous framework to reason about scientific applications anywhere where you try to learn mapping between function spaces instead of finite dimensional spaces. And there is a whole, it's not just one magic trick, it's basically just adapting neural network and seeing how things work at the continuum and how things stay consistent across resolutions. And depending on the problem, we have different tools. So if you're looking at regular grids, you can apply something like the FNO. If you're on a sphere, you can use spherical FNO. Graph neural operator works well on arbitrary geometries, and we also have a lot of work on trying to develop foundation neural operators. So based on transformers, for example, Codano, where we try to combine now elements of transformers and FNO to have something that works across multi-physics problems. So this was a work done in collaboration with many colleagues at NVIDIA. In particular, I work a lot with my colleagues, Nicola Kovacsky, Daniel, Jan Kautz, and many people in Caltech, Anima Anand-Kumar, David Pitt, and many others. So I want to thank them all, and I want to thank you for listening.
Thank you so much, Sean. That was really nice, and also compressed a lot of information in a very clear way in a short amount of time. So thank you very much. I would just reshare my slide for a second before we open the. Thank you. Sorry. Okay. At a certain point, people should see a survey appearing in which we ask again, how did you hear about VOILA? Yeah, and while you people, let's say, answer to the poll, which is important for us because we understand which are the best channels to diffuse our information about our seminars. Now, in general, Jean, thanks a lot because the talk was really nice, and also, I mean, I talk from a perspective of a social scientist, but you have also a different type of expertise in the audience. But it's really nice for us also to show that it should be a datum, so something known, but with the focus that we have on large language model and the AI hype, actually there is development of AI technology that is really has potential to be transformative, because in the end that would transform the way in which we address certain problems like the weather forecast or product development that is machine learning driven, that is AI driven, and it doesn't have to impinge on discussion about super intelligence or awareness, etc. So it's instead is a very technical but useful way of dealing with AI. And what I wanted to, I think I don't know if there are questions. Let me see, but there are questions. But I will use just the chair power to ask a question. That is, so you have been working with different type of data then, and you have been working also with optimization of the algorithm in order to save on memory or save on processing power. In terms of data biting, let's say like when the data is a big cost or is a big problem, this is different for weather prediction or for wind tunnel, etc. So it's like, did you have the data constraint biting more in which domain? So that would be from my side. But before answering, I think we can collect other questions. There is a Sebastian Goffard that has a question. And if you want, you can unmute yourself and ask the question, Sebastian. Or Sebastian.
Yeah, that's fine. Thank you. Thanks again, Jean, for the presentation. Actually, it's going to be quite short. Did you guys also explore the CFD for blood flows as well? Because that's typically, I know a case is that it's quite costly in terms of computation. And it seems to be like definitely an application we could imagine there.
Yeah, it's a great question. So I haven't directly yet. I know that I know some teams. I know some team in Madison was looking at this. It's something that I'm interested in looking at. I know there had been a lot of work on applying for different CFD. I know in Caltech they did some work for catheter design to kind of use CFD to minimize the flow of bacteria upflow to limit the amount of bacteria. So I am not sure how much has been done for blood specifically, but I think it would be very interesting and a perfect use case actually for this. So yeah, if you have interesting problems, yeah, reach out. We're always interested to look at
Yeah, actually, I
problems.
would be happy to share that with you. Maybe we can chat later. But I know a team also in Netherlands, which is actually currently trying to modelize, let's say, the flow without like using full CFD. So yeah, maybe we can reach out later. Would be nice.
Yeah, sounds great.
Thank you very much. Are there other questions or comments? Or compliments? Or, I mean,
Yeah, I guess in the meantime, I can answer also your question, Simone, which was very nice. I didn't really have time to go so much into all the aspects. I was trying to mostly give an overview of how to actually apply things. But indeed, in a lot of problems, we have very limited data, and that's a big difference. In language, you have very large amount of data. And in fact, if you look at the problematics, people are getting worried that they're running out of data to train the large language models on. Same for visual problems. In scientific applications, it's way worse. We have sometimes very limited samples. For weather, we have about 40 years of data, and that's it. You can try to generate data, but it's not always the true distribution. And when you can, it's still very, very costly to generate this data. So one of the things that is important is that neural operators tend to be very sample efficient. So especially when combined with things like tensor decomposition, we can actually train them with a lot less samples than with a transformer. So you could, given infinite amount of information, you could always do something like a vision transformer where you take your input, patchify it. That wouldn't really be resolution invariant, so you would need to do some more work, but you could apply something like a transformer. But if you have limited amount of data, performance will often be a lot better with a neural operator. So one of the nice properties is that they're really sample efficient. So that's one of the main reasons we applied it to a lot of these domains. And in that sense, whether actually we have a lot of data, and there we have another problem that in some of those applications, I was talking with some astrophysicists as well. And there we have another problem. It's not that you don't have enough data, it's that you have too much of it and it's too large to even handle. And so in that case, we shift the problem from being able to train on it to even being able to store it. And so in this case, now you become IO bound. You spend more time reading your data and storing it than actually training your model. And so in this case, there are various things you can do. You can try to distribute training over your entire domain, and each GPU can see just a part of your image. But yeah, I think it's very problem dependent. And one of the strengths of neural operators is that they don't necessarily require as many training samples. But they still will work well in the low data regime.
Fantastic. Thanks a lot. Other questions? In the meantime, I see that also Katarina joined, our co-organizer, together with Lucille and myself.
Maybe a quick question.
Please, Lucille.
Yeah, so just for to get a bit of view. So it's first, thank you so much for your talk, because I think it's very useful also to have to see that targeted models that are really focusing on general yet specific aspects, like here for operators, allow to have some more efficient approaches in terms of data and compute. And you introduced the term of physically inspired neural operators in regards to PIN. Could you maybe tell us whether there's been some really nice applications recently that allowed for these models to really gain performance or data efficiency or generalization in certain applications?
Yeah, thank you. This is a great question. I think, yeah, like this physics-informed neural operators are really nice theoretically. And so the idea is, yeah, you first, as I mentioned, have this data-driven learning phase where you learn an operator mapping between functions based on what you see. So you have a set of training data, you train your operator, and then given a new instance of the problem, you actually use your model to predict the output solution, and you plug that into the equations, into your PDE, and you use that as a loss to fine-tune the model. The problem with that is this PDE loss typically has derivatives of the solution, for example, spatial derivative, either first or second order. And so you need to now be able to estimate those derivatives. So there, one advantage of neural operator is that you can generate high resolution outputs. And so in this case, typically people use finite differences to compute those derivatives, but that can be very inaccurate if the resolution is low. So you need very, very high resolution. That can be problematic. One recent paper we had is called the modified graph neural operator, a modified GNO. And the idea is kind of training a graph neural operator, which now allows you to use autodiff to compute the derivatives you want. And so we had to kind of make sure that the integral in the GNO, if you remember, it's a local integral. And so we had to kind of make sure things were well behaved and that the derivatives were smooth, and so hence the modifying operator. But yeah, basically I would say some modified GNO-based method that allows you to use autograd to compute those derivatives allowed us to be a lot more accurate. And there's also a lot of work in Caltech, for example, using Fourier continuation. So the idea there is you can also compute the derivatives in the Fourier domain. And so we actually just added to the neural operator a Fourier continuation that lets you more accurately compute derivatives in the Fourier domain. So I would say there is a lot of nice work on this. The biggest problem is when you need very, very accurate solutions, like in the order of 1 to the e-8 or 1 e-12, you really need to get very, very accurate derivatives, and their finite differences can be a challenge. And in that case, we want to move towards autograd using a modified GNO or computing the derivatives in the Fourier domain using Fourier continuation.
Thank you very much.
Thank you to both of you. We still have, so as just a reminder, so today we need to close at 5:30, Paris time, of course. But we still have time for a couple of questions in case. I have another one, which is also, once again, very, very generic, but if somebody wants to intervene, would be very happy, because it's an occasion that doesn't occur every day to speak to an expert such as Jean. And let me see if there is yeah, that's well, while people were still thinking, the question I had, it goes very much beyond. I mean, I don't know if you can answer to that, but in a sense, not in terms of capability, but in terms of if it is allowed. So we see increasingly that basic research has been done inside private companies or companies that are connected with university but are not. And for example, I don't know, with my team, we work also on robotics, and we see that NVIDIA, for example, has the Mujoko environment, simulation environment. So there is, these are in a certain sense attempt to explore different application domains that are not only like business model, LLM driven, like. So how did you find but it's not just related to how do we use GPUs in a sense. So how did you find the basic research done in your context? Like, is it we always have this idea of Bell Lab 2.0, you know, like that is a foundational research done in a private context. And yeah, I don't know if you have any insight about that, would be nice.
Yeah, it's an interesting question. Yeah, I guess large language models kind of change a bit the context, and now that you need these very large computational resources to train things. I think it's not so different. It used to be already the case at some point you needed to have large CPU clusters Now you need large GPU clusters. So I feel like in some ways it's just evolving. But as far for NVIDIA research, I think it's been really, really nice in the sense that it's a fairly small fairly small research teams, and most of the work we do is completely open source, and we collaborate a lot with universities. A lot of this work was actually started in Caltech by Animan and Kumar's team, and a lot of my collaborators still work there. So I think it's been really nice in that sense. I don't know, there's always this thing like necessity is the mother of invention. I don't know how true it is here. I think that's true that now you need a lot of computational resources, and in some ways partnering with industry, academia partnering with industry and vice versa is kind of a nice way to do it. Because especially I think when it comes to scientific applications, we need a lot more partnerships. There is, if you look at large language model or just image generation, you can afford to have maybe just a team that simply works on this. I think for these applications, there are so many types of expertises that need to come together that it's not easy for a single team to do it. So you need to have now HPC knowledge. How do you actually keep your GPUs running? How do you orchestrate? How do you have communications between them? You need to have deep learning expertise. How do you actually now train your model? How do you train your neural operator? But you also need deep scientific expertise. You need to actually understand your problem. What are you even trying to model? What kind of data do you want? What are the problems inherent to this? And so it takes a lot more. And I think we're hopefully going to see a lot more collaborations between both industry and academia. And if you look, for example, weather forecasting, that's an example where we collaborated with a lot of different teams. There was a lot of work with the Berkeley lab, a lot of work with Caltech. We have now a whole weather and climate team, which are climate and weather experts. And so I think as we try to apply AI to more useful problems, so all these engineering problems, we're going to hopefully see a lot more of these collaborations. So I'm quite hopeful that together I think when you work on a real problem with real implications, things kind of just end up working out because everyone, if you need to actually get something working, it's very clear whether you're getting somewhere or not.
Nice. Do you have time, Jean, for the last question?
Yeah.
I also like the fact that we went from, very general, very technical, very general, very technical, and also like your positivity on the, nice combination of orchestration, collaboration, plus open science would be really an optimal. So there is a question from Maria that if you want to unmute yourself and ask the question, otherwise we can read it for you. Maria Bernick. Read it, please. Okay. Thank you for the talk. I have a question about the diffusion process, which was shown on the forecast-net schema and which, according to the schema, generates noise variables. Why did you introduce this part inside the model?
Yeah, this is a good question. So actually, one detail, that one is not a diffusion process. So we could use diffusion or stochastic interpolance to learn a probabilistic map from the current state of the atmosphere to some future state. What we did in forecast-net is a little different in that we generated a smooth noise on the sphere, and that was part of the input, and the output was conditioned on this noise. And the reason we did this is that now you can generate an ensemble by just running your model many times with different noises. Or more efficiently, you can just generate a bunch of different samples of this noise. And in simply one forward pass, you can get an entire ensemble. So for each, let's say now each of your sample has input samples has a different noise. You can batch those. So you have a batch of n times the same input conditions with different noises. And as output, you will get in one shot an entire ensemble. So it allows you to generate ensembles much faster. Diffusion, on the other hand, would be a lot more costly in the sense that you would have to actually, denoise n times to get n different ensemble members. So yeah, that's why we conditioned on this noise. And that's why we then had to use something like CRPS to do training, because the model is no longer doing deterministic prediction. is just generating ensembles at each time steps. I hope
Thank
this
you.
answered the question.
Thank you very much, Jean. So, as we are heading towards the end of this VOILA, first of all, before we thank you, I just wanted to, just to remind everybody to stay tuned. So you can scan here the QR code for the website, or follow us on LinkedIn or the YouTube of the recorded events, so you can keep track of what we are doing. And the next event is going to be announced soon, but as we said at the beginning, you can put your email in the website and receive information. Just we can tell you that the topic is going to be open source and security. So once again, we are nicely connected across the topics. So stay tuned with us. Thanks very much to Jean Kossaifi that gave us a very, very nice overview of what it means to use neural operators and how it can be used for scientific applications that really have transformative value for the society and in general for scientific for science and discovery. And yeah, so virtual applauses for you, Jean. And
thank you so much for the invitation. Yeah, I had a great time and great questions.
Thanks a lot. And with everybody, we see each other soon. So take care, have a lovely evening, bonne soirée, and sleep well. And bye.
Thank you very much. Thank you, Jean. Goodbye.
Merci.
Thank you.